Yeah, so if I start with the idea of oxidation numbers, then oxidation numbers are basically coming from how many electrons they can lose, gain, or share. And basically the idea of oxidation state is that if something is, even if it is covalent, what if it was ionic? If something was purely ionic, what would its oxidation state, oxidation number, its valency be? That is the idea of having these different oxidation numbers. So if we move across period 3, here's the thing. The pattern goes like this. So you have sodium. Sodium is +1 when it forms ion. There's only one oxidation number that it does. There's magnesium, that's +2, there's only one. Aluminium +3, only one. Silicon +4, only one. Phosphorus +5, only one. Sulfur +4, +6, both. Chlorine +4, +6, +7. And argon obviously does not do that. Now, this is the idea of what to do. Now, tell me, judging by this, can you take a minute and write the oxides? Write the formula of all the oxides that these things can form.
Sir, how is chlorine's oxidation state +4, +6, and +7?
It does that. I'll quickly talk about the structure of chlorine atom in a bit. उससे पता लग जाएगा कि क्यों ऐसा होता है. So write down the formulas of all the oxides of chlorine or these all things. Sodium, we know when it reacts, it forms Na2O. It's going to be purely ionic. MgO, Al2O3, SiO2, P2O5. Again, what am I doing? I'm doing the cross multiplication thing that we learn about in all of this. This one will be SO2 and SO3. This one would be ClO2, ClO3, Cl2O7. Okay, that is what it can form based on this information. Okay. In fact, that's not the only case. Silicon does have other oxides. Silicon does have Cl2O. It also has Cl2O5. So can you tell me what's the oxidation number of chlorine in here, in this one, Cl2O?
1.
1, it is 1, yes. And that might be difficult to explain using the idea of sharing of electrons and all that. It can be difficult to explain. And we usually sometimes also get oxidation numbers that are half, which are absolutely nonsense when you talk about electrons coming in or electrons going out. You can't have half in it. So the oxidation number theory does go bonkers a little bit sometimes. But over here, this all makes sense. It is all about the structure of chlorine and chlorine's electronegativity playing a role over there. Just recall, whenever you have different non-metals joined together, especially the ones that are very electronegative, you have to remember whatever you want to call it, fungal or whatever. Basically, you're going to assign oxidation numbers in that order. So if you have fluorine and oxygen joined together, you will start by assigning fluorine its oxidation number before you assign it to oxygen. Okay, I will talk about group 17 in detail, and over there I will explain why chlorine does or why it is so versatile. But for now, I want to focus on the hydroxides, the oxides and their properties. Okay, so just bear with me. I know Sameen, you have asked a question, but I will ask you to just bear with me for now. Okay, so the first thing that we need to remember about oxides is there a pattern to the way they react? And yeah, there is a pattern. So sodium, magnesium, aluminum, we know them, they all burn in excess oxygen and they will produce these oxides. So for example, sodium, what's the color of sodium flame? Do you remember this from IGCSE? If somebody has done IGCSE here. If not, okay, remember that in O levels we don't talk about it, but sodium burns with a yellow flame. Okay, so when you burn sodium, it reacts with oxygen, it gives a yellow flame and it produces Na2O. Magnesium burns with a very bright white flame and it produces magnesium oxide. So white flame there. So there's a yellow flame here, white flame here. You need to remember this color white. Okay, aluminium doesn't really react that much. Does anybody remember why aluminium will not burn? If I took a piece of aluminium and tried to burn it, why would it not burn?
So because it has a coating of aluminium oxide around it, which is unreacting.
Very good. It is protected by this layer of aluminum oxide, which is very difficult to pass through for oxygen. But if I break aluminium down into very small powders, like powdery particles, बहुत छोटे-छोटे particles कर दूं, then it will burn and it will again give me a white flame, and it will give me Al2O3, which I can use. In fact, sometimes when we want to burn aluminium, we use an oxidizing agent to burn that, so that even if aluminium reacts with the oxygen in the air, it can burn with the oxygen coming from that oxidizing agent. This reaction is very slow. The silicon is one. Silicon burns very slowly, but it still forms this. That's important if you want to remember. Phosphorus burns with yellow flame again, but this is white, which means you're going to get a smoke of white P2O5 when it burns. Sulfur has a blue flame. So sulfur burns with a blue flame and forms sulfur dioxide. And you then convert sulfur dioxide to sulfur trioxide using a catalyst. Does anyone remember this catalyst?
Vanadium 5 oxide.
5 oxide. And what's the process called?
Contact process.
Contact process, exactly. And the oxides of chlorine, they don't really ask us about the flame and all that. मुझे तो याद भी नहीं है. So yeah, that is the burning of these things. Now, these things have different nature. Sodium oxide is basic. Magnesium oxide is basic. Aluminum oxide is amphoteric. Does anybody remember what amphoteric means?
Like if it's in the presence of a base, it'll behave like an acid. And if it's in the presence of an acid, it'll behave like a base.
Okay. So what should they do with water? You're right. That's what amphoteric things are. But what would it do with water? It depends. कुछ भी कर सकता है. But that's not important. Usually water, pure water के साथ हम react कराते नहीं हैं. There's going to be some impurities, and those impurities will decide what behavior will it show up. Phosphorus oxide is acidic. Silicon dioxide is acidic. Sulfur dioxide is acidic. We know that. And chlorine oxides are also acidic. So do you see a pattern here that from the very left side, this is basic things. And as you go towards the right side, they become acidic. Okay. And that can be confusing if you try to think of Lewis acids. Like Lewis acids are the things that try to accept lone pairs. But why would sulfur trioxide want to accept a lone pair? Or why would chlorine want to accept a lone pair? We'll talk about that. We'll talk about that in a bit. So let's see how they react, these things. So if I put sodium oxide in water, why is this thing basic? The reason it is basic is that if I take sodium oxide and I put it in water, it's going to form sodium hydroxide. Okay. And once it reacts, it does this very alkaline thing that it makes. Similarly, magnesium oxide, if I take that and I react it with water, it will give me magnesium hydroxide. And this thing, do you think it is soluble? Magnesium hydroxide? याद है किसी को? Magnesium hydroxide. We talked about it in O levels. Milk of magnesia कहते हैं इसको. If somebody has acidity and all that, उनको वो कहते हैं कि इनको खा लो. So this is reaction of reaction of oxide with water, reaction of magnesium oxide with water. But I can do the same thing if I take sodium metal itself. Like if I take sodium in water, does anybody remember what it does? Sodium in water. Come on. We know sodium is more reactive than hydrogen. इतनी chemistry तो हमें आती है.
It makes Na2O.
Na2O? No, not really. Basically, you have to think of water as H and OH. So when water reacts, it breaks down and it gives off H positive and OH negative ion. And that is called autoionization of water. And when that happens, sodium being more reactive, why do you think it is more reactive? Think about it from the perspective of group 1. Why is sodium more reactive than hydrogen? In group 1, just for this question, I'm going to say we have hydrogen, lithium, sodium. So judging by this, can you explain why sodium will be more reactive than hydrogen?
Sir, is it because of the shielding effect from the other electrons?
Good. There is shielding effect from the inner shells. This is, remember, this is period 3, this is period 1, which means there is shielding effect in sodium, which pushes the outer electrons away with much greater ease than hydrogen. So when it wants to make positive ion, sodium finds it much easier to do that. And sodium does that. Sodium replaces H positive and makes sodium hydroxide. And that hydrogen has no option but to leave. So it goes away. Okay, we balance this. So that is sodium reacting with water. Magnesium also reacts with water in a similar fashion, but not as dramatically as sodium, because sodium's reaction is very volatile. Sodium is floating around the surface and all that. And the pH that you get at the end is very, very strong. It's 14 for sodium hydroxide, very strong alkaline solution that you get at the end. But with water and magnesium, the things are not that fast. And here's the interesting bit. Magnesium does not replace one hydrogen, it actually replaces both of them. Can you think of a reason why it would do that? It forms MgO. Can you think of a reason why it does that? The idea is really simple. Why was sodium able to replace H positive? Because sodium wants to just lose an electron. And hydrogen is there to gain that electron, and sodium is losing one electron. Hydrogen accepts that one electron and goes away. But magnesium is losing two electrons. So it just distributes them to both the hydrogen atoms and forms a very strong bond with oxygen that's there. Okay, so you get magnesium oxide. What does chlorine do with water? That's a very interesting reaction. The detail of this, we will study that in A2. Like, how exactly does this work? But for now, just try to, I told you, this chapter is, there are many, many holes in there. There are many things that I cannot explain fully right now, because you have to go through the electrophilic substitution reactions or the homolytic fission reaction, hydrolytic fission reaction that we study in organic. So until we do that, we will come back to this. But for now, just remember that this forms HClO and HCl. Now, the reason this reaction is important is because this is a new kind of reaction. We call this disproportionation reaction. We have studied this in redox. Disproportionation. Why is it disproportionation? Because disproportionation reactions are the ones. Does anybody remember what they are? Disproportionation kya hota tha?
Sir, is it when like an element or something with one oxidation state gets splits into things with like two oxidation states?
Yeah, exactly. Same thing. This does a redox reaction, and it has multiple different ending oxidation states. So that's disproportionate. For example, chlorine over here is 0. That's the oxidation state. It's an element. But over here, the oxidation states are different. Over here, it is -1 here. And over here, we will use the Funkel rule, this one. We will use this idea that we will first start by assigning oxygen state to oxygen, and then we'll come to chlorine. So this is -2, this is +1. So based on this, chlorine is +1. So you can see that on one side, chlorine goes from 0 to +1, and on the other side, chlorine goes from 0 to -1. So chlorine is the thing that is oxidizing. Chlorine is the thing that is reducing. So that's disproportionation. And this reaction is useful for a multiple different reason. For example, do you know that we add chlorine compounds or chlorine itself to swimming pools, or we add chlorine to water supplies, like a small measured amount? Because of this thing, because you're adding chlorine to water and it's going to react with that water and it's going to produce HCl and HClO, both of them acids. So what are they going to do with any bacteria that's there? They're going to break down, वो जो उसने बड़ी प्यारी सी अपनी सेल वॉल बनाई हुई है ना, उसको उन्होंने तोड़ के तबाह कर देना. So now that acid is going to break down the cell wall of that bacteria, and yeah, story khatam uski. That's why we use it. That's why we use it in swimming pools. And one reason why swimming pools are slightly green is because of this. There are other reasons as well. Mainly उसका color इसकी वजह से नहीं हो सकता. Can you think of a reason why a swimming pool should not be green? Because you have added chlorine to it. Chlorine is yellow-green if it is not reacting. If it has reacted, it's created HCl and HClO. Acids are colorless. So the green color only comes from the chlorine that did not react. All right, so this thing, HCl, HClO, this very acidic. So you can clearly see when metals react with water in here in period 3, they're making highly alkaline substances. And when non-metals are reacting, like in the case of chlorine, it's producing HCl, okay, which is highly acidic. So it's complete 180-degree flip that they've done. So from left to right, when you react them with water, they start by adding making alkaline, then slightly alkaline, then suddenly with chlorine it is fully acidic. Potassium, sulfur, and chlorine, they do not reduce water, like in the sense that you cannot get hydrogen gas from there. In fact, phosphorus and sulfur don't even react with water. Okay. Similarly, aluminium and silicon, again, they don't react with water. Again, can you think of a reason why? Why doesn't aluminium react with water? We studied this in O levels. Wahi, same reason. It has a layer of oxide. Why doesn't silicon react with water? What should we, how should we try to answer this question? We should think about what group silicon is in. Silicon is in the group of carbon. Tetrahedral structure of diamond comes to mind. Silicon has a similar structure. It's a giant covalent structure. Water की क्या मजाल के वो उस giant covalent structure को तोड़ के उससे react कर सके? Water is unable to do that. Doesn't have enough energy to do that. With steam, sure, but with just plain cold water, not gonna happen. Okay, so silicon doesn't react with water. Silicon dioxide doesn't react with water. Why? Because again, you have to break the giant covalent bond that you have. Okay, so that's the thing with silicon. Okay, so we've talked about magnesium, we've talked about chlorine. We now know that silicon and aluminum don't react with water. Sulfur and phosphorus don't react with water, and they do not produce hydrogen gas. But chlorine, when it reacts, it produces HCl and HClO. It disproportionates into an acidic solution. Okay, so we have that. So from left to right, what's happening is that the reaction with water is slowing down. With sodium, it's really fast. With magnesium, it's not that fast. With aluminum, it just dies down. Then it starts again. There is with steam, silicon react. With phosphorus and sulfur, they do not react again. But chlorine does react to give us an acidic solution. So the reaction dies down, the strength, the intensity of the reaction dies down, and then it starts to rise again. The reasons are again the same. It all has to do with how many electrons they need. Sodium needs to lose 1 electron. Chlorine needs to gain 1 electron. 1 electron, that's it. So they're ready to do any reaction they need. But magnesium has other challenges. There's 2 electrons that it needs to lose. So it still manages to do that. Aluminium has this layer which stops it from doing that. Silicon has this giant structure. It stops it from doing that. With phosphorus, sulfur, now things are again taking momentum. And with chlorine, they end up and you have a very fast reaction. So there is going to be always this pattern in all the reactions that we see. Okay. We have talked about oxides. So for example, over here, what kind of bonding we see? Again, the bonding is similar to the pattern that we've seen in period 2. Sodium oxide, basic ionic compound. Magnesium oxide, ionic compound, and it is basic. Aluminum oxide, again, mostly ionic, slightly covalent. Okay. Again, the reasons for covalent structure, we don't need to go into that for now. Silicon dioxide, purely covalent, giant covalent structure. Remember from O levels, quartz, it's called sand bolte the, but sand nahi hai ye, this is quartz. Okay, quartz is the thing that you see in many gemstones and all that. Okay, reaction is super slow, and then we have phosphorus. There is P2O5, but P2O5 also exists as P4O10. Which is its dimer form. Do you remember dimer from covalent bonding? Where it forms dative bond to make a bigger structure. That's what P2O5 does. Then you have sulfur dioxide, sulfur trioxide, molecular covalent structures. P4O10 is also molecular, by the way. And they're all acidic. Phosphorus oxide, sulfur dioxide, sulfur trioxide, silicon dioxide, they're all acidic. But aluminum oxide is amphoteric. The properties of these obviously depend on the kind of bonding they have. So for example, if I ask you, will molten magnesium oxide conduct electricity? What will your answer be? Will molten magnesium oxide conduct electricity? Come on, magnesium oxide is ionic. When it melts, it has magnesium ions, oxide ions. It will conduct electricity. क्यों नहीं करेगा वो? करेगा. What about sulfur dioxide? Will it conduct electricity? Absolutely not. Why? No free electrons, no matter what it does, and ions तो है नहीं. The only forces that it has is intermolecular forces, van der Waals forces, London dispersion forces. In fact, यहाँ पे तो हमारे पास permanent dipoles हैं. So permanent dipole की वजह से the melting point is higher than you would expect in others, but still no conduction. Melting point. Okay, here's the question: will the melting point of aluminum oxide be greater, or will it be greater for magnesium oxide? In fact, ये question तो A levels में आ ही नहीं सकता. Will the melting point be greater for magnesium oxide or sodium oxide? ये question A levels में आएगा. Basic circle. Tell me, will the melting point be higher for magnesium oxide or sodium oxide? कौन सा?
Magnesium oxide.
Why? Good question. Correct answer. क्यों?
Sir, I don't know if this is the right word, but it has a higher charge density.
It is the right word. It is the right word. It has higher charge density. Both the ions have higher charge density. Don't say it does not have high charge density. Say the ions have higher charge density. So yeah, the strength of forces is going to be much stronger, right? So you need more energy to break them. No wonder magnesium oxide is used as a refractory lining for furnaces. लोग उठा के फर्नेस में रख देते हैं उसको, फर्नेस को बचाने के लिए उस आग से, क्योंकि magnesium oxide withstands that. Will it be a good idea to use magnesium oxide to make ceramic? It is a good idea. People agree. Acha, now I'm going to tell you something about the reaction, the nature of the oxide. अब ये थोड़ा सा A level से आगे की बात है, थोड़ी सी, ज़्यादा नहीं. So here's the thing. In ionic oxides like sodium oxide, we have sodium ion and oxide ion. This is what it breaks up. And what does it produce? When it reacts with water, it takes water's H positive ion. So let me take this thing and react it with water. It's going to take the hydrogen from water and form what? If oxide accepts one H positive, what will it become? I have water. Water gives me H positive. It reacts with it. I shouldn't draw the curly arrow, but it makes hydroxide ion. And how many of them? एक तो जो इन दोनों के मिलने से बना, और एक वो जो पहले से था. So you are getting two hydroxide ions. That's what happens with sodium. That's what happens with magnesium. But हमने तो अभी देखा कि वो magnesium oxide बनता है, क्योंकि फिर वो breakdown होकर magnesium oxide बनता है. But again, थोड़ा सा बोले A level के आगे की बात है. Now, why doesn't this happen when I have sulfur dioxide? वहाँ पे इसको क्या मसला है? If I take sulfur dioxide or if I take silicon dioxide, वहाँ पे ये हरकत क्यों नहीं कर रहा? The answer is really, really simple. Silicon dioxide will not do this because the reason this happens is because you have oxide ion. You don't have that oxide ion in silicon dioxide.
So I don't get this.
So remember that you have oxide ion in ionic compounds. That oxide ion can accept H from water. It can attract that H positive. But in covalent oxides, you don't have that. You don't have any oxide. You don't have that oxide. So उससे क्या होगा? It can't do that. It can't do the same thing. It can't accept H positive from water. Now, remember the structure of water was this. You had a lone pair on this side and that side. In covalent substances, if they cannot accept H positive like that, there's something else that they can do. It can form dative bond. If it can't form ionic reaction, it can't accept H positive like that. it can still form dative bond, and water has plenty of opportunity to form dative bond. So what does it do? Silicon dioxide or any other non-metal oxide that I'm going to get, carbon dioxide ho sakta hai. I take that thing and I add it to water. It's going to go and form dative bond with this oxygen. And what does that do? It makes oxygen lose this H positive, it cut it off. So now you have a hydroxide with a dative bond and an H positive gone. And that is why non-metal oxides are acidic. So if I were to, I know thoda sa confusing ho gaya hoga. So if I were to write an equation for this, when you have metallic oxides, you have the oxide ion. This oxide ion with water accepts H positive and gives me two hydroxides. So if you have ion, it's going to do that. But if you don't have ions, if you have some compound with covalent bonding, non-metal oxide isko, and MO likhte hain. When it reacts with water, it's going to form dative bond with it, with the oxygen part, of course. And it's going to form, the OH is going to come and form dative bond. And the H positive is going to go away. This OH will still have a negative ion.
Repeat after the 2OH, like for the non-metals, can you repeat?
The idea is simple. Water can break down into two parts. Water can form H positive and OH negative. The H positive can react with oxide and form hydroxide. So if you have H positive and if you have oxide ion, they can react and make hydroxide ions. Okay, so if you have oxide ion, that's going to happen. But if you don't have that, then the non-metal is going to form dative bond with the hydroxide from water. And that's why it will be acidic. Let me do it again. Let's start from the very beginning. Water is this. Water has two main things. It can break down, give us H positive and hydroxide. Now, what are these things good at? Hydrogen ion can react with other things that have lone pair on them and react in an acid-base reaction. Hydroxide can do the same thing. It's a base. It has lone pair. It can donate that lone pair. Now, here's what happens. Oxide ion can get this thing because it's an ion. It attracts the other ion. It's a negative ion. That's a positive ion. It attracts it, makes hydroxide. That makes two of them. There's one hydroxide that is made from the metal oxide, and there's one hydroxide that is made from water. So with sodium, you're going to get sodium hydroxide. With magnesium, you're going to get magnesium hydroxide. But with non-metals don't have ions. Non-metals can't accept H positive. So kya karenge wo? They can form dative bond with hydroxide. So metals give us oxide which targets this. Non-metal oxides target this, which is why when carbon dioxide is dissolved in water, it is acidic because it targets this thing, it reacts with this thing, and H positive is free to go away, which is why the solution becomes acidic. When silicon dioxide reacts with water, if it reacts with water, it reacts not with the H positive part, but with the hydroxide part, okay? And water becomes acidic. When phosphorus oxide, P4O10, reacts with water, it does not react with H positive part, it reacts with the hydroxide part. And that hydroxide part reacts with it, and H positive is free to go, which is why it's acidic. When sulfur dioxide reacts with water, it reacts with the hydroxide part because it can form the dative bond with it. And that means H positive is again free to go. When sulfur trioxide reacts with water, same thing, it forms dative bond with hydroxide and H positive is free to go, which means this is going to be acidic.
Yes, sir.
Perfect. Sulfur dioxide, sulfur trioxide, P4O10. आपको A levels में वो पढ़ाते क्या हैं? आपको A levels में ना equation दे देंगे. मैं आपको equations को लिख देता हूँ. For example, वो आपसे कहेंगे कि magnesium oxide, when I add it to water, it forms magnesium hydroxide. Why is this doing this? मतलब आपको A levels में you're not required to explain it. But do you understand why this is happening? It is happening because water broke down. Before water reacts, water has to become H positive and OH negative. And this oxide ion in there targeted the H positive, made hydroxide. So this broke down, made H positive, made OH negative. This oxide targeted this and made another hydroxide. That is why you're getting magnesium hydroxide as this. Plenty of hydroxides there. When sodium oxide goes in water, same thing. Water breaks down, gives H positive, OH negative. This oxide ion targets this because it has lone pair to give to H positive. It does an acid-base reaction. And that is why we say that these are basic substances. They are giving lone pair. Notice there's a lone pair on oxide that's going to go towards H positive. And that's why you're getting sodium hydroxides, two of them. When I'll talk about aluminum oxide in a bit. It's amphoteric, तो उसका मैं बताता हूँ अभी आपको. When silicon dioxide goes in water, what does it do? When this goes in water, it doesn't, water again breaks down. Water has to break down. But because there is no ion in silicon dioxide can only make dative bond with this. Ion तो है नहीं, H positive तो accept कर नहीं सकता. That is why it forms a compound with it, जिसका formula as such you don't need to know. वो ये होता है. It just gets SiO3 negative. Again, formula आपको याद करने की जरूरत नहीं. And loses the H positives away, which is why this thing is acidic. Acha, this equation is required. So P4O10, the phosphorus oxide, when this reacts with water, I'm not balancing the equation at the moment. Okay, I just want to focus on the concept. What does it do? It's gonna react with the OH again. Okay, so this water breaks down, gives me OH negative, H positive, and this P4O10 reacts with OH. Okay, and forms through two-step reaction. It forms phosphate ion, and obviously there's plenty of H positive to lose. So this is acidic. Okay. When sulfur dioxide goes in water, it gives OH negative, it gives H positive. It doesn't have oxide ion, so it can't attack H positive. But what it can do is it can react with this thing, make dative bond, and eventually lose all the H positive and make what? Sulfur with 3 oxygen and a -2 charge. Sulfite ion, and plenty of hydrogen go away. When sulfur trioxide goes in water, it does the same thing. It reacts with OH negative, makes it lose all the H and makes sulfate with plenty of hydrogen ions. No wonder these things are acid. अब आपकी syllabus में you're just required to remember it. But I think understanding helps. Now let me talk about aluminium oxide. Aluminium oxide क्या करता है? Aluminium oxide is amphoteric, which means it can accept H positive, it can donate H positive. It can do both of them. So it depends what are you reacting it in presence of. Like if you're reacting it when you have HCl or H positive. So what I'm going to do now is that I'm going to add water, but also some H positive ions, which means I have acidic solution. In acidic solution, aluminium oxide is going to react as a base, okay, in presence of H positive. So it's going to react as a base and it's going to form aluminium hydroxide. But sometimes aluminium hydroxide forms this and sometimes it forms this. Again, ये आपके A levels में नहीं है, ठीक है? ये पूरी equation आपके A levels में नहीं है. A levels में आपने क्या याद रखना है? That in presence of acids, aluminium ion is going to form. और अगर आपका acid HCl है ना, it's going to react with that. ठीक है? मैं आपको बताता हूँ. Let's suppose मेरे पास Al2O3 है. मतलब this thing then reacts with H positive और सारा एक reaction करती है. लेकिन आपने याद क्या करना है? If I reacted with acid, then aluminium ion which forms, it's going to react with this chlorine, okay, and form AlCl3 and obviously water. But if I have aluminium oxide and I reacted with sodium hydroxide, then aluminium is going to react with that hydroxide and you are going to get this thing. So what happens? You get aluminium hydroxide with a negative charge. Do you see any positive charge? Sodium is a positive charge. So you get this ion which reacts with sodium again and makes us sodium aluminum hydrate. Again, iski theory isn't required in elements. So I know you're not happy about it. Okay? This thing is called sodium aluminum tetrahydrate. A2 में जाके आप इसको थोड़ा सा स्टडी करेंगे और तब मैं आपको डिटेल में बताऊंगा कि ये ऐसा क्यों है और ये क्या करता है. But for now, just knowing that water can break down into H positive and hydroxides, and that H positive can react with oxide to make hydroxide helps understand why metal oxides are basic. They are producing hydroxides. And why are non-metal oxide acidic? Because they are accepting lone pair from hydroxide ion. They are acting as an base themselves, losing a lot of, they're acting as an acid themselves and losing a lot of H positive in the process, which is why they're all acidic, non-metal oxides. And aluminum oxide is one thing that is amphoteric in here. Okay.